course. Today I want to talk about shared state concurrency. First, a few seconds of respect for the Ukrainians who are still fighting for their freedom and ours. And today I want to talk about shared state concurrency. But now we're getting close to the end. So to the brave souls who are here in front of me, I say bravo for being here. And to guys who are watching me on video, you should have been here, but I will explain everything on the video. We have seen 3 so far paradigms for making concurrent programs. Deterministic data flow, multi-agent programming, and another one, this was actually mostly in the previous course, deterministic data flow where you add ports where you need them. These are the best ones. Deterministic data flow is the best one, but it's only deterministic. So this is the best one, as you can see here. Multi-agent programming, it allows non-determinism, interacting with the real world. And we saw how to do real systems with this, and we saw a really nice, very good language called Erlang, which is used to do very hard stuff using this paradigm. And the final one, which is the best one, but still no language supports it, it's interesting, is where you have deterministic data flow, but you just add ports where you need it. Remember we saw client-server, where you just have to add one port, where the clients talk to the server, and all the rest is functional. This one is the best one for writing concurrent programs. But so far no language is supporting this one, maybe someday. Today, we're going to see a 4th paradigm for concurrent programming called shared state concurrency. This is where, instead of using threads and ports for multi-agent, we use threads and cells together. Cells, mutable states, variables that you can update. Okay? And we will see 3 important concepts. Locks is the basic one. Critical sections, building atomic actions. Monitors, which is how threads can coordinate, work together. And transactions is for it's for fault tolerant for databases where you can do updatable actions that can actually abort. So if there's a problem, the transaction restores the state. So those are the 3 variations, but they're all based on locks. Locks, transactions, monitors. Locks are important. Transactions are a very good concept for databases and fault tolerance. But monitors are very bad, ugly things, very smelly. You don't want to use them. They're very bad. And it's very interesting because the guy who invented multi-agent programming, or one of the guys, who was named Tony Hoare, was also the guy who invented monitors. This was around 1970. Of course, in those days, it was very hard to see the future. So monitors are concurrency on shared state, and also port objects are for concurrency multi-agent. But monitors are very bad, nasty things. But I'm still going to teach them because there's a lot of legacy code using them. So Java uses them, and they're called synchronized objects. So these are really ugly, bad. I cannot emphasize how bad monitors are. The trash can is too good for them, okay? But I'm still going to devote a lecture to them. So I will waste 2 hours of this course talking to you about monitors. But that's going to be next week. Today I want to talk about shared state concurrency, okay? So you see, I have a strong opinion on this, on what is the best and what is not good, huh? Everything is based on cells. I'm going to very quickly refresh so that you have everything in your mind on the cells. Mutable state, so shared state concurrency bases on mutable state. So this is variables you can update multiple times. This is used a lot, so I'm not going to explain the intuition. Many languages support this, Java, Python, etc. In this course, that concept, we call it a cell, because the word variable is massively overused. In mathematics, a variable is just a placeholder for a value in a mathematical expression. You cannot update it. In computing, well, there's many things that are called variables. It could be the identifier, it could be a variable in memory, or it could be a cell. Okay? So when I say a variable that you can update, I will always call it a cell. And a cell is two things. It's a box that has an identity and a content. So it's two things. The name of the box is a constant, which is in memory, in processor architectures, it's often called the address. If you have a memory, a cell, or a piece of memory, a memory word, the content is what's inside that box. And in this course, the content will be always a variable in the single assignment store. Okay? So two things. A cell, therefore, is not like a variable in the single assignment store, which is just one thing, Okay. And the cell has three operations. I refresh you so you can create a cell. So cells are never automatic. And in a language like Java, it's all the time you define functions, methods, whatever, all the attributes, all will automatically create cells for you without having to say anything. That's actually very bad, because cells are nasty things. You want to avoid them. So here we have to create them explicitly. Create a new cell with initial content A, and C is bound to the name of the cell. So that's a constant. C is a constant. And then you have assignment operation, which replaces the cell's content by a new content, B. And then you have a read operation, which I also call access. So Z is bound to the content of the cell, but this content is not changed. Okay? So those are the three operations: creation, assignment, and access. Okay? And refreshing, you have notion of aliasing. Because you have the name and the content that are separate, you can have two different cells with the same content, or you can have two different identifiers pointing to the same cell. So here you have a cell identifier X, so variable X. So when I say this is the box. X is actually bound to the name of the box, and 0 is the content. So here, the box will have content 5. If I do Y is equal to X, then the name of the box will be also in Y. That means if I change the cell, the content, X will also see the change. Okay, so this is called aliasing. This is something you have because you separate the name and the content. And this is a big problem. So X and Y, you can call them also pointers, for example. So languages with pointers, it's like, they're like this. They're doing like this. If I now update the content Y to 10, that means the cell content will be 10, but X is the same cell. X and Y have the same name, so the content of X is also 10. So if I read X and I compare it to 10, it will be true. Also, X and Y are the same cell. So if I do X equal Y, it's also true because they are the same constant. But here I'm not looking at the content. So you see, you have to be very careful distinguishing the name of the cell and the content of the cell. Okay? The semantics of this beast, let me very simply remind you, this is added to the kernel language. Now we will have two stores. Before we had the variable store, which I call sigma 1, which contains variables and their bindings. If they're bound, they can also be unbound. T equal 10, X equal C. And now we have a new store called the cell store, which contains pairs. So here, for example, x colon t, where x is the name of a cell. So you see x is actually a variable in sigma 1, bound to the name of the cell, and t is actually a variable in sigma 1, which is the content. So you can actually have cells pointing to themselves, of course. You could have x colon x. So the content of the cell is the name of the cell itself. This is like pointer pointing to itself. That's very reasonable, no problem. So this is completely general. You can use it in any way. These two are variables. But the first one, the only condition is that the first one has to be bound to the name of the cell. That's what you get when you call new cell, okay? And I will use Greek letters, small Greek letters. The name of x will be, see, this is a constant, and I give it this weird Greek name because the language already has other constants. It has numbers and atoms, which are also constants. But c is not a number, it's not an integer, a real number, floating point, it's not an atom. In fact, you cannot print this number. It's actually the same kind of constant as the name constant we use for abstract data types. It's actually an unforgeable constant. And also y here will be another cell. So here I have zeta, another Greek letter. And the content of x is t, and the content of y is w. Okay, so you see that's completely the semantics, and the operations work like this. So assume I have an environment where x, y, z refer to little x, little y, little z. If I do x colon equal big Z, that will change x colon t into x colon little z. And if I do access y, this will return the variable little w. Okay, so that's how they work. Okay, so that's cells. That refreshes the memory. This is the thing we're going to use together with threads, and which will be complicated. And I'll show you why. There is a fourth operation called exchange, which is we added especially for concurrency. It's an operation of 3 arguments, a cell and 2 variables. This exchange is the same as doing x gets the content of cell, c, and c is bound to y after that. So these 2 operations are separate operations, but the exchange is a single operation that does 2 things. And so the difference between these 2 is that the scheduler can never stop in the middle for exchange. These 2 operations are atomic, which means it behaves as if it were one indivisible action. That means the scheduler is either begin before or after. It will never stop in the middle. You will never suspend in the middle. You will never see an intermediate state. Okay? Exchange does read and write atomically. Okay? This is very important for concurrent programs. In fact, in very old books, if you get a computer science book from like 1970s, you can do all what I'm showing today without exchange. Theoretically, you don't need exchange. You can build blocks with only atomic read and write. But it's much more complicated. There is an algorithm called Decker's algorithm. It's written like this with 2 Ks, which, if you are curious, you can look up. Decker's algorithm, which shows you how to build blocks using only read and write. This is a pretty complicated algorithm. And when people started making concurrent programs, like in the 60s and 70s, it started like this. Then they realized, no, not good. We don't want to do like this, actually. And that's when this atomic read and write actually makes it much, much, much simpler. So this is much better operation for concurrency. Okay, so that's kind of the history. If you're curious, you can see this is like a historical thing. Nobody uses this algorithm today, but in the olden days it was a famous algorithm for doing locks using only read and write. Okay? Today we will use exchange, and when we implement locks, like reentrant locks, which I will show you today, we will do it using exchange. And with exchange, it's actually easy, okay? There's no reason to not use exchange. Decker's algorithm is the other way, which I will not show. It's a waste of time. And in fact, this is so important that the actual processor architecture have machine instructions for this operation. Okay? It's not just a language invention. It's something that's added to all the machine instructions because concurrency is implemented in the hardware. Threads are supported in the hardware with interrupts. And it has to be efficient. But of course, it's not usually called exchange. If you look at like Intel or ARM processors or whatever, there will always be instructions, but they have different kinds of names. But it's always a read and a write. So maybe it's test and swap. So test is a read and swap is a write. And swap is where you exchange a value in a register with a value in memory, or test and set. Now test is reading a bit, and set is setting the bit. Compare and swap, similar. So they all have names like that, something like that, but they're both doing read and write, okay? So there's many variations of this for certain kinds of efficiency reasons, but it's always read and write together, okay? So that's the fourth operation, and today we will use that, and you'll see with exchange, it's actually reasonable, okay? Okay. Now, let me talk a little bit about shared state concurrency and how to do it, and basically how to build large atomic actions. Okay? Okay, so shared state concurrency, we define it. It's the programming paradigm where you have both threads and cells, and you use them together in the same program. Okay? So this is widely used, this is very old paradigm. Almost all major languages, Java, C++, C#, whatever, there are languages that are going away from this, finally. I mean, Erlang goes away from this, but languages like Go, and there's other languages now going away, and hopefully in the future more and more languages will go away from this. So there's a language called Scala, which is built on top of the Java virtual machine, which is both functional and object-oriented. It's like a more modern version of Java, and it has support for multi-agent, what they call actor programming. It has a subsystem called akka, which is used for multi-agent in Scala. Of course, in Java, multi-agent, there's really no support for that. Okay, so it's widely used, but despite that, it's very hard. It's like people keep pounding their head against the wall, and that hurts. But why do they keep doing it? Because they've always been doing it like that. So it's kind of weird. There is no logical reason to use this paradigm, except maybe for transactions, but not for monitors. There's no technical reason to use it. The only reason is legacy code, okay? And the reason, and it's because it's so hard. And I will tell you why it's hard. So you will understand why it's hard. So here's why it is so hard. Here I explain the technical reason why shared state concurrency is so difficult. Assume we have two threads, T1 and T2, so the time is going from left to right, and each of these little things is an operation on a cell. So both of the threads are referencing the cell, same cell, C. And these little operations, A0, A1, B0, B1, are operations on C. They can be either read or write operations, okay, on the cell. Now, how does this execute? So assume each thread does n operations. Here I have 10, and here I have 9, but let's say each thread, does n operations on C. Now how does this execute? Well, the scheduler will flip back and forth. This has an interleaving semantics. So the scheduler will flip back and forth to execute T1 and T2. But the scheduler is very free to do that. And the question is, how many possible interleavings are there in this? So for example, here A0 is first, and then B0, B1, then A1, A2, A3, then B2, B3, B4. So the scheduler has made a choice. But how many possible choices are there if each thread does n operations? Well, you can compute that. It's combinatorics. Assume we have 2n operations. That means in the timeline there's actually 2n slots. Okay, 2n. And the a's are in n of those, and the b's are in the other n. That means the a's will choose n positions out of 2n. Okay? So you have from 0 to 2n minus 1. The a's will choose n. And the b's will have only one, there's only one possibility left for the b's. There will be n slots that open, and the b's go in there. That means the number of possible interleavings is 2n choose n. This is a combinatoric. It's also sometimes written C 2nn, something like that. There's another way to write it with C, but this is the usual notation. So you've seen that, right? You've seen some combinatorics. So you know what this, so we can compute that. So that's 2n factorial divided by n factorial squared. We can actually approximate this. We use Stirling's formula. So there's a formula approximating the factorial, which is n over e to the power n times the square root of 2 pi n. So that's all we need. You can do more accurate, but that's not necessary here. That's good enough. If we fill in this here, this number is approximately 2 to the power 2n over square root of pi n. So square root of pi n does not go up very fast when n increases. But here we have this little n in the exponent, 2 to the power 2n. So this is exponential in n. So the number of possible interleavings for a program that is running, and the longer it runs, the more you have. It's exponential, and all of them have to be correct. No matter what the scheduler chooses, the program should not be buggy. So how do you write a program where you have an exponential number of schedules that all have to be correct? Okay? Okay, so the number of interleavings is exponential in the number of operations. We assume the program is correct, so all interleavings must be correct. That's very nasty, actually. Even if you have a very small number of incorrect ones, the system will break. Even if 1 out of 1,000,000 is incorrect, then your program will crash very fast. Okay, there is no small number. Any number that's different from 0 here will cause your system to crash very fast. Okay? And you cannot rely on scheduler timing. You never can rely on that, because the timing depends on the whole environment, and weird things can happen. The famous example, which I mentioned before, there's many examples, but this one, there's in the 1970s, this radiation machine which has a processor and a keyboard and irradiating cancer cells to kill them. If you type very fast on the keyboard, this kind of makes the scheduler do something different, and it exposes a bug that was not exposed during the testing, because the testing was done by typing slowly on the keyboard. And so patients died because of that. So that's not, you cannot rely on that. There's 2 other ways to test correctness. So testing, like I said, you can only check a small fraction of these exponential interleavings. But you have to do it anyway, It's still essential, Also, verification. Verification is good. Model checking. So there's a course by my colleague Jacques Pecheur, which tells you how to do verification. That's also very important, because it's It can catch bugs that are otherwise hard to catch, but it's limited. Again, because the number of interleavings is exponential. The amount of computation is very large. Now there's many techniques and tricks for reducing data, for making model checking efficient. But still you cannot completely kill that beast, okay? The exponentiality still shows, so you can only verify parts or smaller programs, but still very good technique, huh? And real systems have been verified, like the automatic metro lines in Paris are all verified, completely verified. That was a big work, actually. Also, things like the Intel processors, the arithmetic operations in Intel processors are very complex. Also the digital logic has been verified. There was a famous bug some years ago in the Intel divide operation, which you think there's millions of people using it. How could there be a bug in divide? But there was a bug in the divide, and for certain numbers, certain kinds of numbers, basically it would crash the processor. Well, at that point they hadn't actually completely verified it, okay? So that was really a strong hint that you should verify. See, because they're pushing very hard efficiency, so it gets very complicated. So this can be a good. So both testing and verification are still very important, but they're not enough. You need the third. You need a third pillar. There's three things. The third one is design. Your program has to be correct by design. The design has to be such that if you are following the design, it will be correct. And that's what I talk about today. Correctness by design, okay? Okay, so that's important. But still, these two, testing, of course, are very important. There's many testing tools, and verification is also very important, but they're not enough. You need also to do correctness by design, of course. It seems like no-brainer, huh? If I want to build an airplane that doesn't crash, the design should be a design that doesn't crash, okay? It seems very logical. But somehow software is attracting people who are not so rational. So that's important to say that you have to design things correctly. Okay, so what does that mean? Designing a program, a concurrent program to be correct? Well, basically, it all comes down to the interleavings, these exponential number of interleavings. How do you make sure they're all correct? Well, the basic technique is to reduce the number of interleavings. Instead of this big, large exponential number, we turn it into a much smaller number. And each of those, that smaller number can be checked by hand or by tool. Okay? And three paradigms have different ways to do this. So this is the technique, reduce the number of interleavings. In the three paradigms, so the two we saw before and the one we see today, this is always the technique we use. Deterministic data flow is somehow the best, without ports, because all interleavings give the same result. So the interleavings have no more effect. So it's like there's no interleavings. All interleavings give the same result. That is, of course, the best. If you have a paradigm that forces, because of the paradigm, that the result is always the same, no matter how the scheduler chooses, that's pretty strong, of course, But deterministic data flow does that. That, of course, is the best, if you can do that. And then there's no worries. But you cannot do it for the whole program, so you need to add a small number of ports. And for those, you have to check the interleavings. So you use deterministic data flow most of the time, so no interleavings. So they're all the same. And for the ports, you have to check the interleavings. But usually the number of ports is very small. So the interleavings, there's very few. In the client server, it's where the message arrives. There's one port. So typically you need a port whenever you interact with the real world. Inside of the system, Every part of the system that you are building, that you control, you don't need port. The non-determinism that comes with ports comes because you have no control, and that only comes when you interact with the real world, okay? So that's the best if you can do it. So far, no language is supporting that, unfortunately. But there's a second one, which is pretty good too. This is the multi-agent, the message passing with port objects. So each port object has one thread inside, and it receives a message, it does something, and then it receives another message. So the interleavings are very not small. It's only in between message. So like what I call method executions. You receive a message, you execute a method, and then you wait for the next message. So that whole method is executed sequentially. There's no interleavings, it's sequential. So internally, the port objects are sequential. This really makes the reasoning simple, okay? This is why that multi-agent programming is so nice. It really, really reduces the number of interleavings, okay? Because the interleaving only comes between messages and not for every single operation, okay? You see that? And this is successfully used, of course, So Erlang relies on that. So you can write correct Erlang programs pretty easily. And the third one, this is the one we do today. We have shared cells, many threads. We build big atomic actions. So the single operation is too small. So we're going to group them together and build large atomic actions. A big one that's atomic, and then another one. So the scheduler will not stop in the middle. And that will reduce the interleaving. So that's the basic technique for all of them, but we're going to use it today on this one. Okay? See how it works, huh? Okay. So the main technique for building correct shared state concurrent programs is to build big atomic actions. And so the basic concept is a big atomic action, which is called a lock. You have a whole bunch of operations. So here I have a lock. It's a piece of code, huh? I have a bunch of operations inside, but the lock is like a box, and I enter it and I can exit. This is one atomic, it's like one operation for the scheduler. The scheduler will never stop inside there. It's either before or after. So that really reduces the number of interleavings, huh? So that is the concept. That's what we're going to look at today. And then there's two refinements of that, monitor and transaction. So they are both locks, but with something extra added. So a lock just groups them, but a monitor adds something more. If I have a data structure that's used by multiple threads, like let's say I have a buffer, and I put an element in, and I take an element out. So the thread that takes the element out has to wait until the other one puts an element in. So the two threads are kind of coordinating with each other. So threads sometimes have to wait. So if the thread is taking an element out, and there's nothing in there, in the buffer, then it has to wait. So a monitor is like a lock plus ability of threads to wait on conditions. So these things called wait sets. So that the monitor is for collaboration between threads. And the final one is called a transaction. This is where instead of just exiting, the transaction has two possible exits. So the commit corresponds to exit, it's just a normal execution, but there's another exit called abort, which means that the whole operation is cancelled. So the state at the abort is the same state as the input, so it's still atomic. So it's like nothing happened. So this is very important for things like database stored on a disk. If you're doing something and the disk crashes, and you can't do the operation, the only logical thing to do then is to cancel it completely if you want the program to be correct. So you add this abort. So transaction adds the ability of the atomic action to abort. Okay? So those are the three things. So there's kind of like a hierarchy here. Actually, there's many variations of these concepts. Monitors, there's many variations. Transactions, there's many variations. There's a huge literature. You can buy books that show you hundreds of kinds of transactions. So here is kind of what it looks like from the distance. The simplest thing is called a simple lock. The most basic atomic action, which I will explain. A more refined one is called the reentrant lock. This is where the thread that's inside the lock can enter the same lock again. You will see, which is not possible in a simple lock. And then you have monitor, where you have what's called a gating mechanism. So threads can allow other threads to go in or not. So the threads are collaborating. And then you have what's called a lightweight transaction. This is a transaction in memory. So it's not on disk. You have things called, for example, STM, software transactional memory, where the transaction is purely in memory. But then you have the full transaction, which has what's called asset properties, atomic consistent isolation and durability. So this one is stable even with crashes. So this one will use disk. Okay? And there's many variations which I will not talk about, but you can find them easily on Wikipedia and so on. Okay? So this is what we're going to talk about in the course. Okay? So this is kind of a hierarchy. Each step below is the same as above plus something more. So the monitor is basically a reentrant lock. The lightweight transaction is also a reentrant lock. So everything is based on reentrant locks. Okay, so that's kind of the organization of what we're going to talk about. Today I want to talk about locks. Next week we'll talk about monitors. And the week after we talk about transactions. Okay, so how do you prove things? Okay, so we don't have enough time in this course to really go through many proofs. But I'll just give you the idea. So I have a program that uses locks. It uses these big atomic actions. And if it's well designed, it's actually kind of interesting. Remember we talked about abstractions, where the abstraction has a boundary? Well, usually it's a good idea that the locks are also kind of having the same boundaries. Okay? So the atomic actions are often going to be the same boundaries as the abstractions. That's a very reasonable way of doing things. So the correctness of concurrency is very similar to the correctness of the abstractions themselves. Okay? So that's, well, usually what you do. And then there's two parts. So each atomic action is correct by itself. So I enter and I exit. And this is usually, there's an invariant. So for example, I have a buffer, and the invariant is that there's a correct representation of some number of elements. And if I do put, then afterwards, there will be correct representation of elements plus the new element. Okay, so there's an invariant, and the invariant is preserved. That means when I enter, it's true. If you assume it's true on entering, it will also be true on exit. So you have to prove that. So that's something you prove separately for each atomic action. So that's pretty easy. Now it's just a little proof for each lock. And then the sequence. So the real program is going to be executing a lot of these atomic actions. And there you have to prove that the program is actually doing something reasonable. Basically, that it's making progress. And this is called liveness. So it's basically, you can see that the atomic action by themselves is like safety. Remember safety and liveness? A little bit? Well, you'll see it in other places. So safety basically means that you don't do anything wrong. And liveness means that you're actually going forward. You're making progress. So the sequence of actions is somehow going forward. So we know that the invariant will always be maintained. That's fine. But we have to prove that the program is actually advancing, it's going forward. So we have to prove liveness. So we need some kind of a measure of progress, how much work has been done, and that number has to increase, okay, in time. So remember the lift control system? We can prove liveness properties. The lift will always eventually go to the lift that is first in the schedule and correctly update the schedule. So the lift, they're port objects, so you can prove each time it receives a message you have a correct update of the state. And then you can prove that the sequencing of these atomic actions is correct. The lift will always eventually go to the lift that's first in the schedule, and it will then remove that one, it will update the schedule. Okay? So that's a liveness property. Okay? So this is how you prove it if you have big atomic actions. And you see, the big atomic actions gives meaning to the program. You know, single operation on cells in the difficult, when I show difficulty, the single operations, when you do an assignment or an update, doesn't really mean anything. It's very low level. The meaning is big blocks. When you do a whole bunch of things, it means something. I've added something to the buffer. Or I have completed a transaction or something. So that has meaning. It has a high-level meaning. So that's why this is actually a good way of doing things. Okay, so that's kind of all very theoretical. Now let's go to logs and explain how they work. Okay, logs. It's actually in the book if you want to see more, section 803. So a lock is a language concept that guarantees that only one thread, at most one thread, will be running in a specific part of the program. And that part is called a critical section. If another thread tries to enter that part of the program, it will suspend. It will wait at the boundary until the thread that's inside leaves. And if you do that, then the action is atomic. Okay? So here's an example. So this is code, and there's a lock L. So the same lock, so this is protected by L, and this is protected by L. So if a thread comes in here, let's say there's a thread executing here, then no other thread can enter. Notice the two pieces of code can be separate. The same lock can protect many pieces all over. It doesn't have to be just one piece. So if there's a thread here inside, and another thread tries to get in this part, it will wait at the boundary until this thread leaves. Okay? And then this thread can go in. If there's only one thread inside at the same time, at most, that means the scheduler can put that thread to sleep, but then it can just wake it up. So there will be no switching of threads, so the action will be atomic. Okay? The scheduler can never switch one thread to another inside the critical section. Okay, see how it works? So that's how it works, and we can implement that. We implement it actually using exchange and cells. You'll see. So we can introduce an abstraction. So I'll show you how to implement it. With exchange, we can implement that in the language. We don't need anything new. No magic. We can implement locks using cells and using exchange. Okay? So here's an abstraction. So new lock creates a new lock, L. We can also test whether L is a lock. Okay? And we can store locks inside of data structures. Okay? A lock is like a piece of data, actually. And then there's the guarding. Lock L, then statement N. So this is the OS syntax of this. So OS provides locks, like many languages provide locks as part of the language. Okay? So this guards the statement lock L. And you can have multiple statements protected by the same lock. Lock L, then statement, you can put it in many places, and all of those statements together are protected by the lock. Okay? If no thread is in any statement guarded by a lock, then any thread can enter. If there is a thread inside, another thread will wait. So basically it suspends. So it stops right there if it attempts to enter a guard statement while there's another thread inside. Okay? But then there's another property. Assume the thread is inside the lock. It's inside. And inside, it runs into another lock L statement. Okay? So it's like this. So let's say I have lock L. Then, and I'm running stuff. And what if I have another lock L statement inside here? So the thread is running here. What does it do? Well, it's already inside, so the reentrant lock is allowed to enter again. Okay? The lock statement can be nested. So the property is inside or outside. So once you're inside, the thread is inside, you can enter again. So that's what a reentrant lock can do. You also have a thing called a simple lock, which doesn't do that, but it's easier to implement. So when we show the implementation, we will show first the simple lock, and then we show how to make it reentrant. Okay? So in the simple lock, this would be deadlocker. The simple lock, if the thread enters here, it would stop here. So the simple lock would actually do a deadlock. The program would actually stop, and nothing can start this thread up again. Whereas a reentrant lock would just continue, and when it leaves here at the end, and it keeps going, it's still inside actually. It only actually leaves when it leaves the outermost end. Okay? So the reentrant lock is actually the right concept. Simple lock is too simple. Okay? So that's how the abstraction works. So I'm going to show you now some code with that to show you how it's done. And you can see I love cues because I'm going to show you again a cue abstraction. Very similar to the cue we saw earlier in the course, but this time it's a concurrent cue. Many threads can put elements in, many threads can take elements out. So we'll have a concurrent cue, and we'll implement it. Okay? Assuming we have cells and locks. So here we have a cue. So this greenish sequence is a cue with a cue has a front and a back. So A is in front and then B and C. So this has three elements. If I do insert D operation on this cue, then I add D to the back. Okay? And if I delete an element from a cue, I will delete it from the front. So you add in the back and you delete from the front. So if I delete X, which is unbound, then the A will be removed and X will be bound to A. So that's an output. Huh? So that's the cue. So insert adds X to the back, and delete X removes an element from the front and binds it to X. So it's very symmetrical. So we're going to implement this. So I'm not going to do a very complicated implementation. I'm going to reuse one that we saw before. I'm going to implement it as a difference list, so that it's declarative actually. So here I have the cue. The cue here is bound to this tuple. It's a 3 tuple. So the 3 is the number of elements in the cue. And here I have the actual cue. So this is a difference list. So A, B, C with an unbound variable B, and then the second part is the B. So this is a difference list. Remember, the advantage of difference list is that you can append elements in constant time. But it's ephemeral, but that's okay. That's okay because, I mean, in a concurrent system you can call the queue from many threads, but there will always only be one version, okay? That's typical in a stateful system. When I have a queue and I update it, then I have a new queue, but the old one has disappeared, okay? So in a stateful system, all abstractions are kind of ephemeral by default, So this will be ephemeral, but that's okay, because we have a stateful system. So if I insert D, then I bind the B here to D bar B2, and I replace the B by B2. So the new Q looks like this, and the 3 becomes 4, 3 plus 1. So this has D in the back. If I delete X, then I will bind X to the first element, A, and I will replace this part by the one where I remove the first element, so BCD, B2. So you see how it works, huh? You can do insert and delete very easily with this. Okay? Now this Q will be stored in a cell, and the cell will be protected by a lock, because we can do this insert from many threads. So we have to be careful that there's no problem. We have to build big atomic actions. Okay? So we will put the operations inside a lock. So let me show you the code now for this with locks. So assuming we have locks, so here's the new Q. This defines insert and delete, and you return this record here, which has these two operations, insert and delete. Insert X and delete X, like I showed. Now here I have inside a cell and a lock. I will define a cell, so the original cell is going to have content 0xx, so that's an empty Q, huh? And L is a lock. And here is how I define insert and delete. Now I have to read the content of the cell, and I have to update it. So I have two operations, a read and update. But I don't want the scheduler to stop in the middle, because that's inconsistent. So I put them in a lock. So lock L, and here this one also is predicted with lock. You see the same lock protects both. That means if I have multiple threads doing insert and delete, then they will wait nicely, and each thread will only execute one of these if nobody is inside anywhere, huh? Okay? See how it works, huh? So here I read, so I'm actually using a bind, this bind as logical kind of operation. I define N, F, and B2. Okay? I will read the cell and bind it to this, which means I bind N, I bind F, and I bind this. This automatically binds the end to X bar B2, and the new cell will be N plus 1, and the F, and the B, which this B is bound to this, will be replaced. So that is the insert, and the delete is kind of the opposite. So N, X bar F2B is bound to C. So this will bind X to the front. So that's the result here. And the new Q will have N minus 1, and it will have F2 here. So the X is removed, and the B is the same. Okay. So I have read and write, read and write. So this is two operations. So if I don't put the lock end, it's buggy, huh? If I don't put the lock end, and if I use it in multiple threads, then maybe the scheduler will put this thread to sleep here, and then the other one will do it, and then both of them will do assignments, and the value will be wrong. Huh? So you have to combine these two in a big atomic action, and the invariant is that the content of the Q is determined by all the preceding inserts and deletes. So all the elements I've inserted will be in there, except for the elements I've deleted, which will be gone. So it's like all the inserts minus deletes is what will be inside. That's the invariant. Okay? And I can prove that this will maintain the invariant. So there I'm good, huh? There I'm very good. Okay? So there you see how to use logs. Okay, let me make a small break, and after the break, I will show you how to implement the logs. That's when it gets really interesting, huh? Well, so now I will, first let me show you a small example of execution. Let me execute this cube here.
Okay, so this one is supposed to start with a 1.4. Let me put the so this is a Q. This is the Q, same Q I showed you. And now we can actually define a Q. So I can insert A into this Q, and I can remove A.
And you can see the A there. Amazing, huh?
So it actually works.
Okay. I always want to show real code and not just code on slides
to show really things executing. So this is real code, it works. Okay.
Now, let me say something about reentrancy. I show you an example to really, so you really understand why it has to be reentrant. So technically you want to nest the locks. But let's say I want to make an operation, insert 2, which inserts 2 elements into the queue because somehow they're connected. These 2 elements, there may be 2 users of something and I want them to stay together. And I have nothing in between. So I do insert X and insert Y. But that's not good enough, of course, because the scheduler can stop in the middle. I have to guarantee that X and Y will be together in the queue. And the only way to do that is to put the lock here. Okay, lock L, end. But the insert also has a lock inside, and this one too. And when we call insert X, the thread is already inside the lock, so the lock has to be reentrant. So you can see reentrance is really important when you're building abstractions. With the reentrancy, it's very natural, you can do whatever you want. Okay? Okay, here I have a slide where I explain that it's possible to delete elements before they are inserted. But let me not go too much on this. It's because I'm using because the variable store has logical formulas. It's not just like bindings as assignments, they're actually logic. It's logic. And that means logic can be done in any order. If I insert, then I do bindings. If I delete, I do bindings. But bindings can be done in any order because it's just a logical formula at the end. That means you can actually delete before inserting, and it works fine. So this is not an accident. The system is actually doing logic programming, and this only shows you a small piece of the power you get from logic programming. So the main logic programming language, still today, is called Prolog. This language is 50 years old. 50 years, 1972, and still going strong. Pretty amazing. And a couple of weeks ago, on the 10th of November, there was a symposium on the 50th anniversary of Prolog in Paris. I attended that, since I'm an old Prolog guy, okay? I did my PhD in Prolog. And Prolog is still going strong. Why is that? Why is this very old thing, 50 years old, still being used today? It's under the radar, but many applications are using Prolog, okay? Because it does logic programming, and this only gives you a small piece of the power. So this has some very powerful abilities, and the fact that you can delete before inserting is actually just a small example of the kind of power you can have. Okay, so that's all I want to say. A little extra shout out to Prolog. Okay, here's another implementation of the queue without locks. This is, now I show you exchange. Okay, remember exchange CXY is the same as read and write. So basically, you read the old and you update. So the exchange does both. And with that, we can actually implement the queue without locks. Look at the insert operation. Because in the queue we only need to do one read and one write. One read and one write. So you can combine them as an exchange. If you look at the queue here, I read the old value and I update it. So it's a very simple thing. Bigger abstractions will need more. But this is simple, so we can actually implement it using exchange. And we don't need logs. So this is the old value, QNF x bar v2. This is bound to the old value, and this is the new value. Notice there is a small trick here. The n+1 operation has to be done after. Because if you do it before, the n is not bound yet, and it will block, okay, because of data flow. If I so I will actually put an unbound variable here, m, and then I will say m is equal to n+1. So it has to be done after, because we have to know n. Here also, the n-1 has to be done after. Otherwise, it will block, okay? So this works for the queue, because we only do one read and one write. But queue is a very simple abstraction. Real abstractions will be doing lots of updates, so it doesn't work anymore. So I'm just showing you this to show you one example of a program using exchange. So you can use exchange directly if you only do one read and one write. Okay, now let's implement locks. This is where things get very interesting. We will implement the locks using cells and exchange. So inside the lock code, we will have cell and exchange. So I'll do 3 steps that get successively more complicated. I'll first show you a simple lock, so non-reentrant. To make it reentrant, we have to do something more, because when a thread tries to go in, we have to check whether it's already in. And the only way to do that is if that threads have identities. So we have to know which thread is in. So that requires a little bit of code, so I'll do that later. And there's another thing, which is exception handling. If I'm in a lock, and I divide by 0 and I raise an exception, the exception will leave the context. But I also have to leave the lock. So raising an exception is another way to exit the lock. That means the lock has to exit whenever I do an exception. So that actually has to be part of the code. This will be done using the try finally. So I need to do code for that. And so the final one is reentrant lock with exception handling. This is what all systems do. This is the standard lock used by everybody, Java, whatever. They're all using this, reentrant lock with exception handling. And we will implement locks using a technique called token passing. So how do you implement the lock? I have many threads trying to get in. And how does that work? How does a thread go in? And once a thread is in, the others don't go in. And they have to wait. How do we implement that? Well, the technique is called token passing. So there's a token, which is a thing that there's only one of these things. Un jeton in French. It's a thing, and in the system there's only one of them. And each lock has a token, and in order to enter the critical section of the lock, you need the token. The thread needs a token. But there's only one token. So if there's a thread already inside, then that one has the token, and the one on the outside will not have the token. Okay? If the thread tries to get in, and it doesn't have the token, it waits. It says, I want the token, please give it to me, and it will wait there until it gets the token. Okay? And when a thread leaves the critical section, it will forward the token to the next thread that's waiting. So there's like a relay running course where you have a token, a baton, some kind of a stick I'm running, and then I pass it to the next guy, and then that guy starts running. So when the thread leaves the critical section, it gives the token to the next thread waiting. So the threads are waiting in a sequence. They're waiting in a line, They're not it's not messy. They're all waiting in a line, and the first one will get the token. It goes in, and when it goes out, it gives the token to the next one, and so on. So it's using this technique, and we implement this technique using cells. So the cell somehow keeps track of which thread is waiting for the token, and I'll show you how it works. So here's the code. Okay, so this is a simple lock. The token is here, so this is a cell. And unit is a constant, and unit means if the value of the cell is a bound to something like unit, then I have the token. And here is the lock. Notice this is using higher order programming. So it's lock of P, where P is a zero argument procedure. So instead of doing lock L statement, the statement is inside the higher order. So I implement this using higher order. The statement P is just a zero argument procedure, and the statement is inside there. Okay? So it's a higher order program. And here's how it works. So here is the statement, and it's surrounded by these two operations. Wait old and new equal unit. So wait old is waiting for the token, and new unit is giving the token to the next guy. And exchange is how the token is managed. So it's like people waiting in line, okay? And I think it's good to make a picture of how it works. Because each time a thread executes lock, it will run exchange. So the exchange is done outside of the critical section. So this is the critical section. So all the threads will run exchange. And the order that they go in is determined by the order that they do exchange. And because exchange is atomic, each thread will do the exchange, and the scheduler somehow chooses the order of the threads. But we don't care, it doesn't matter what the order is. There will be some order. It depends on the order that they execute exchange. Okay? So that's how it works. So let me show you how it works. Let's say we have a bunch of threads. T1, T2, T3, and so on. Threads that want to get in. Okay? Now, the first one. So we have a lock. We have this lock, which is lock P. So let me do it like this. Proc. So here's a statement that we want to execute. End. So this corresponds to lock L, then statement end. Okay? It's only syntax, so the semantics is exactly the same. It's only syntactic sugar, this lock L. So all languages that have locks will give you some syntactic sugar, but it's basically just higher order programming. Okay? Now I do exchange. So I have this token. So the thread T1 does the exchange. So it gets old. The old content is unit, and it has a new variable. And so the new content of the cell in the token is new. Since this is a constant, it goes in. So the first one is constant, so the first thread goes in. Okay, it's executing P. So the first thread does wait old. So this executes fine, and it starts running P. So it's here. And eventually it will do this, but not yet. Okay, now, so this one is running. Now the second thread comes, and it runs this. What happens? Well, the second thread will run exchange, and it will get an old, but actually it's the same as this new. So this is a new variable, this is the new content, So the second thread will get this variable from the exchange, but it's the same as new one, and it's the same variable. And it will wait on old 2. This is old 1, let's call it new 1. So, new 2 with units. So it waits on old 2, but old 2 is still unbound. Okay, and it also, there's a new 1, new 2. Let me give another piece of chalk. Let me just show you a third thread so that you can see how it's making a line of threads. So let's say so this thread now is waiting here. Okay, T2 is waiting here. T1 is executing P. Okay, see that? T1 is in here somewhere, it's doing stuff. But since new is unbound, T2 is still waiting, it's just waiting here. Now T3 comes along and does an exchange. So T3 has a variable old 3 and new 3, but old 3 is the same as new 2. Okay, so it will wait on old 3, P here, and here new 3 is unit. Okay, so what does T3 do? Well, T3 comes here, it gets old 3, but old 3 is unbound, so it just waits here. You see how it's working? It's important to understand. I expect you to really understand how it works, huh? So T1 is now running. Now I'm use a different color. T1 is running, T2 is waiting here, and T3 is waiting here. Now let's say T1 finishes P1 and it exits here. And it binds new 1 to unit. Well, new 1 is the same variable as old 2, so that means T2 will now start running in P2. You see, when T1 leaves, it's essentially passing the token to T2, and T2 can now start running P. See how it works? So T1 is out now, it's doing something else, it's gone. T2 is now running P, and T3, well, new 2 is still unbound, so T3 is still waiting. Yeah?
So it's possible to exchange unbound?
Absolutely.
Unbound, okay.
A variable can be bound or unbound. Exchange will replace one content by another, and the content of a cell can be an unbound variable. So we're using the data flow property to make this work. Okay? So let me get another color, if I can find another color here. Life is tough. I have green here. Let me use green now. Hopefully you can see it. So now we have T2 running here, and T3 is waiting. Okay? And if there would be a T4, assume there's a T4 coming in, it would also wait, because the old 4 would be the same as new 3, yeah? So you can have many threads waiting, yeah? But here there's T3 waiting. Now assume T2 finishes P, and it does this. So this is supposed to be a green arrow, huh? New 2 is equal to unit. That causes, so new 2 is the same as old 3. It's the same variable in memory. And the wait old 3 will then continue. And now T3 will start running P. So T2 is out. T1 is out already a long time ago. T2 leaves, is out. And now T3 comes in. But T4 is still waiting. So you see, so the token is the status of this variable. So T1 starts by having the token. It does new 1 equal unit, and this passes the token to T2. And then when T2 is done, it passes the token to T3 and so on. See how it works? This is probably the easiest way to implement the lock. Okay? If you want to implement the lock without data flow, it's much harder. So this is basically a completely correct implementation of a lock. Now this one is not reentrant, because what if T1 now, so T2 is running here, what if inside this P, there's another lock, okay? There's another call to this. It's possible, huh? Everything's possible. This P can have this. If that happens, T2 will do another exchange, and it will wait. There's nothing special. Any thread trying to get in, which doesn't have will try to get the token. So the exchange doesn't know that T2 already has it, huh? So this is not reentrant, huh? If T2 tries to get in again here, it will wait, and basically the whole system is blocked forever then, huh? Okay? So this is not reentrant, huh? You see? Okay. Good. It's a nice piece of code, huh? Isn't it? Beautiful. Okay, let's add exception handling to this. That's very easy actually. What happens if the statement inside P raises an exception? Well, we still have to leave, okay? If T2 inside here raises an exception, we still have to pass the token, of course, because we're leaving the critical section. The way to do that is to put new equal unit, to use try finally. So try finally, this is something that will always be executed, even if you either raise or not raise, huh? So all languages with exceptions have something like this, huh? Try finally. So this passes the token to the next thread, even if P raises an exception. So this new equal unit is always executed, okay, when you leave. So that's it for exceptions. That's pretty easy, huh? Right? Now let's try to make it reentrant. So this is the real thing. How do you make it reentrant? Well, right now, any thread that tries to get in will do an exchange. Even if it's already in, it will do an exchange. Okay? But somehow we have to avoid that. If it's already in, we should not do an exchange. We should immediately just start running P, actually. We don't need to do this exchange and wait if it's already in. Okay? So the only way to do that, we need a new concept. Threads need to have identities. When I create a thread, I have to know which thread is in. Okay? Somehow the thread needs some kind of a name. So that the system has to provide that. That's actually easy if you know that you need it, huh? Because a thread is just in memory. A data structure has registers and a stack, huh? But you can give it a name too, huh? So the thread has to have identity for this. So that's a new concept. So a reentrant lock needs to know which thread is inside. It needs to know the thread's identity. Because you know there's a thread inside, you should have to say, is it me? Okay, it has to say, is it the same as me? So you need to know the thread's identity. So in Oz you have a function called thread.this, which returns the thread's identity. But other languages will have something. Depends on the language. But so thread has an identity. So the procedure lock now is written like this. So this part is the same as before. Okay, this is the whole bit with exchange and wait and the try finally and so on. But here I have now, first I want to check, is the thread that's inside the same as me? If thread.this is equal to the content of current thread, so I need another cell. I have to store somewhere the name of the thread that's already in there, right? So this is a second cell called current thread, let's say. So unit means there's no thread, because unit is not the name of any thread. It's just some random constant. So it starts out that nobody is in. Okay? So if there's another thread in, so let's say a thread goes in. So here's the wait and the new unit. So that's the critical section. Before executing P, I will assign this. Current thread becomes thread.this. That means inside of P, I know that the current thread is this thread. Okay? And when I leave, there's no thread, so current thread becomes unit again. So when I'm running P, there's actually, this is the thread inside. Okay? And here, if the thread tries to get in again, it compares its own identity, thread.this, with what's in current thread, and if it's equal, that means I'm already in. I don't have to do all this garbage of bookkeeping of trying to get in. I'm in already. So it just runs P. Doesn't have to do any of this. It's in. The whole bit of getting in here and of leaving only has to be done once. Once you're in, and you don't have to do anything special. So it can just immediately run P, okay? And it actually doesn't even have to do the try finally stuff, because all of this running P, it's actually it's inside here. If this P raises an exception, I will come here. I will come to the outermost, wherever it's running here, I will come. So I just run P. That's it. Okay? So you see, the new thing is you have to manage this current thread, and after you get in. So wait old is very important. This is the barrier. This is where you get in. Once you get in, and before you execute P, you assign current thread. And then, before you go out, so new equal unit means you're out, you assign current thread back to some value that says nobody is in, okay? Now this is very tricky. You have to do it exactly in this order, okay? What can go wrong? So these two statements have to be in this order. If they're switched, your program is buggy. Basically, if they're switched, what happens? So new equal unit means you go out. That means once you're out, the current thread will still think you're in. And if another thread tries to get in, so that's a problem, okay? So what can go wrong? So you should try to imagine a buggy scenario. So this is an exercise for you. If I switch these two statements, you have to imagine a nasty scheduler. So the scheduler is a bad guy. How can the scheduler make your program go really bad if I switch these two? So in the way it's written now, no matter what the scheduler does, the program is right. It will never go wrong. But if I switch these two, the scheduler can make it go bad, okay? So debugging is important. So you have to be able to answer these questions. So to be very clear, these could be exam questions, okay? What can go wrong if these two instructions are switched? What can go wrong if these two are switched? So here's the hint. Wait old, that's where you enter it. New unit, that's where you exit. Everything between wait old and new unit is inside. And everything on the other side is outside. So what happens if you change the current thread outside of the critical section? Bad things can happen. That means you think something is in there, but it's not that thing, okay? So if you switch these two, you will update the current thread outside. Here also, if you switch these two, you will update it outside. So wait old, new equal unit is very important. It is the boundary of the critical section. And anything between that is inside. So anything in between that, you're guaranteed there will be only one thread running this. So this current thread gets thread.this. You're guaranteed that only one thread will do this and the same thread will run P. That's the guarantee that the critical section gives you. But if you switch them, you don't have that guarantee anymore. Okay, see that? So you have to be able to imagine what can go wrong if the program is not rightly written. So this program, the way it's written here, everything is done exactly in the correct order. So the critical section is between wait and new. The exchange is done before. It has to be done before, not after. If it's done after the wait, the system will deadlock, yeah? Can't be done after. Has to be done before. That means it's like getting a ticket. When you go to Midi Station, you want to buy a ticket, you get one of these papers with a number on it. That's the exchange. And if many people try to get in the critical section, they will all have a ticket, and the order will be the order that they wait in line. Okay? So the exchange is getting a ticket. And the wait old is when a counter, guichet, becomes available. So that's the wait old. Okay? So those are two separate things. So you have to, this something you have to really understand how it works. Okay? Then you really understand something if you understand that. Okay. So that's it. Now you know how to implement reentrant locks using token passing. It's an example of a non-trivial concurrent programmer. So you see how we designed it, piece by piece, bit by bit, simple lock, exception, reentrancy, and we end up with this, which is completely correct in a concurrent system. Okay? So you have to understand why, okay? So the picture under on the board is important. Okay, now let's go to another thing. Now I want to introduce a really new thing, a different thing, called Tuple Spaces. So a tuple space is a funny concept. It's a thing that's somehow in between message passing and shared state. How is that possible? It's a very interesting concept. But you can use it also to write concurrent programs. So it's kind of like locks, but a little bit different. Okay. So a tuple space is a multi-set of tuples. And let me make a picture of that. So you can see what's going on. And I explain it because many systems use this concept. Systems, for example, what are called publish-subscribe systems, pub-sub, are actually using tuple space concept. Okay? So this is actually a very useful concept. So here I have a tuple space. This is just a set, so it's a multi-set. Multi-set means that the same thing can be in there more than once. So here is a tuple, here is a tuple, here's another tuple, here is the same tuple again. So you can have a bunch of tuples in there, and these tuples are actually like tokens. Once you put a tuple in there, it's a thing that goes in the tuple space. So they really behave like tokens. So what I showed you before with token passing, in tuple space, you actually have the tokens in your hand, in a sense. So here is the abstraction. You have the multi-set, so you have a bunch of tuples. So the tuples are like tokens. You have write T. So you add the tuple to the tuple space. So this puts a token in the tuple space. It adds one new thing. So even if the tuple T is already in there, it goes in it again. Okay? Each token actually has an existence. Okay? And then you can also remove a token. Read LT. So this one uses kind of pattern matching. This removes a token, but it kind of synchronizes. So it waits until there's at least one tuple with label L, and then it removes one. So in this tuple space, for example, so let's say this one is called TS. If I do TS, read AT, it will wait until there's a tuple with label A. But there's three of them, and then it will remove one of them. So maybe it will remove this one. So maybe it removes this one. But the other two will still be there. So tuples are things. You add one, you have one more. You remove one, you have one less. They are things with existence. Okay. So this is the read. And so it actually waits. So it's a synchronization. So if there's no tuple with label A, then it waits. Okay. So you can see I now have kind of a concurrent abstraction on these tuples. And there's also a version of read which is non-blocking read, which 3 arguments, L, T, and B. Same as read, but it returns immediately. And B is a Boolean. And B is equal to false if there's no tuple with label L. Otherwise, if there is one, B is equal to true. So you see this one is checking whether there's a tuple, and it doesn't wait. So there's 2 variations of the read. There's a blocking and a non-blocking version. Okay? So you can see this is like the token concept is important. So the tokens are real things. Whereas in the previous one, I modeled the tokens using these data flow variables. Here, the tokens are real tokens in this concept. This concept was first invented, to get you some history, in 1985. This concept by a computer scientist called David Galerter, and he called it Linda for some reason. Maybe that was the name of his girlfriend. I have no idea. So it was called Linda. But the read operation did pattern matching. So the read can actually be very sophisticated. It can wait until there's a certain pattern. If you want to, you can make it more sophisticated. Okay? So that's tuple space. So you see, it's a very simple thing, huh? It's basically a bunch of tokens you can put in and take out tokens. Okay? There's another name for this. Sometimes people talk about coordination model. Sounds like a weird name. That's when a person says that, it's exactly the same as a tuple space. So when you see this is a coordination model, it basically means it has tuples that you can put in and take out. A language that supports tuple spaces is called a coordination language. So this is a funny name, but it's just a synonym for tuple space, just to give you the connection. And this is actually used a lot in what's called publish-subscribe systems. So a publish-subscribe system is basically a big tuple space, and you can subscribe to items. Let's say I'm interested in news about Tesla cars or something. And then publishers put in tokens, which are little news items on Tesla. And there's other news items on Ford, on Mercedes, on Rolls-Royce, but I'm not interested in those. I only want the Tesla ones. So when I read from it, I only want Tesla tuples. That's why you have this pattern matching. And you can have many readers. So you have this huge distributed tuple space, and you can subscribe to news items, and you can also publish news items. This is called publish-subscribe. It's kind of message passing system. It's kind of like a mail system, but it's not sending mail to people, but to topics. I send mail to Tesla topic, and I can subscribe to Tesla topic, or Rolls-Royce topic, or whatever. So it's like email, except that you're not sending mail to people, but to special things called topics, the names of the tuples. So that's an interesting abstraction. So, but this is interesting. This is actually a combination of shared state and message passing. So it's kind of like shared state because many threads can access the same tuple space. So it's like a memory, okay? But it's not really the same as a memory because you can never update the tuples. You can only add new tuples or remove tuples. So the tuples are declarative, and it's like message passing because you can send and receive tuples. So adding a tuple is like a send, removing a tuple is like a receive, okay? So it's kind of an interesting in-between concept. But it's actually much better than shared state. Huh? It actually has a lot of the goodness of message passing. And the basic difference, it's very interesting. So with message passing, the sender knows the receiver. I send a message to you, and I know your name. But with tuple spaces, the sender does not know the receiver. The sender sends a message, puts a tuple, and the receiver can be anybody who takes that tuple out. So the sender does not know the receiver. So it's like sending mail where anybody can receive it. You don't know who. And sometimes that's useful, huh? Like pub/sub or printer queues. I want to print a file, but I don't care which printer. So I put a print request, and all the printers will take out print requests. So I don't care which printer receives it, okay? So it's like message passing, except the sender does not know the receiver. Okay? So let me show you a program with this. We can actually program the queue, our famous queue, the queue that I love so much. We can implement it using tuple space. Okay? But it doesn't need the tuple space. We will put it, we will do a read and a write. So we put a tuple in, and we remove a tuple. So the queue state is in a tuple. We take it out, we update, and we put a new tuple in. But you don't need a lock, because tuples are things that exist, that you need. You put in a tuple, you have it. When you remove it, it's not there anymore. So when you read a tuple, it's like entering critical section. If there's one tuple, only one thread can remove it. The second thread will not see the tuple. So you don't need a lock. It's tuple space. So this gives us three kind of nice implementations. You can compare the queue with the lock, the queue with exchange, it doesn't need lock, and the queue with tuple space. So let me show you now the code of the queue with tuple space. Same queue as before, same interface, but you have one tuple in the tuple space. So this tuple space is not very big. It only has one tuple in there, okay? So that's okay. When I do an insert, I read the tuple, which is this, which basically contains the state of the queue. I bind it to nf x bar v2, and then I write the new state, n plus 1 f v2. Okay? And the delete also reads the state and writes the new state. So you have two tuple operations. But still you don't need a lock. Because if a second thread, let's say you do the first one, you do insert, you start by reading. If somebody else wants to do delete, they will block here. Because the read here, the tuple is out. So there's no more tuple inside. So the read will wait until this guy puts in the tuple again. So you automatically have like synchronization. You see that? So that's kind of a neat concept. Very elegant. The problem is it's not as efficient as reentrant blocks. To do it like this, you really have to manage this tuple space thing, which is like a complicated data structure. So it's by far not as efficient, but for pub/sub systems, it's quite okay. Okay? Let me just finish by showing you how tuple spaces can be implemented. You have a multi-set of tuples. How do you implement that? Well, you can implement it using three things. A lock, you need one lock inside it, a dictionary, which I tell you what it is, and a concurrent queue. So I showed you how to do a queue with tuple space, but to do the tuple space you need a queue, okay? It's interesting, huh? So here's a dictionary. A dictionary is just a hash table, where you have keys and values. So you can look up the values. You can add new ones or remove, so there's many operations. But basically you can look up the value, and the key is going to be the label of the tuple. And the value, this will be a queue, and it will be all the tuples with that label. So if we have a tuple with label A, for example, and if there's three of them, then we have a queue with those three elements. Okay? So the tuple operations will insert and delete elements in the queue, and if you insert a tuple and there's no label, then you will add a label, and if the queue becomes empty, you can actually remove this entry. The dictionary is a dynamic hash table. You can expand and shrink. So this lets you implement tuple space. Okay, so that's tuple spaces. Tuple space is kind of a nice abstraction. It's usually used for big applications, distributed things like PubSub. It's usually not used for small programs because you can see this is more expensive than a reentrant log. Reentrant logs are extremely efficient things. Okay, so that's kind of the end for today. Shared state concurrency we saw, combining threads and cells, but it's hard. The number of interleavings is exponential. The operations. Solution, build large atomic actions to reduce the interleavings. And three kinds are locks, monitors, and transactions. Tuple space is also a way of doing similar things to locks, okay? But also to communicate data. And today I showed locks, and next week I'll show monitors and then transactions. And that's all for today. Thank you. Voilà.